In this video, we're going to take a look at how powerful power series can be. We'll look at several different applications in which power series help us to solve problems that we might have had difficulty solving otherwise. Let's start by using power series to evaluate a limit. So we're going to take the limit as x approaches 0 of sine x minus x cosine x over x to the third. We know that we can write sine of x as x minus x cubed over 3 plus x to the fifth over 3 factorial times plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on and so forth. Similarly, we can write the cosine of x as 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and so on and so forth. When we multiply cosine of x by x, we get x minus x cubed over 2 factorial plus x to the fifth over 4 factorial minus x to the seventh over 6 factorial, and so on and so forth. When we subtract sine x minus cosine x minus x cosine x, we get x minus x, which is 0, and then we get negative x cubed over 3 factorial plus x cubed over 2 factorial because of the distributing the negative, and then we'll get plus x to the fifth over 5 factorial minus x to the fifth over 4 factorial minus x to the seventh over 7 factorial plus x to the seventh over 6 factorial, and so on and so forth. Dividing that all by x to the third, we get sine x minus x cosine x over x cubed is now negative 1 over 3 factorial plus 1 over 2 factorial plus x squared over 5 factorial minus x squared over 4 factorial minus x to the fifth over 7 factorial plus x to the fifth over 6 factorial, and so on and so forth. But if we take the limit now as x approaches 0 of that expression, we'll see that all of the terms except for the first two become 0. So we get negative 1 over 3 factorial plus 1 over 2 factorial, which is negative 1/6 plus 1/2, which is positive 1/3. All right, let's take a look at this series we've got here. We've got the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. And maybe you realize by now that this is the series for the function cosine of x. Let's look at it piecewise. If we start writing out the terms of this, we get 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and so on and so forth for all of the even powers of x. Which means that when we take the derivative of that series, we can do that term by term. And since it's cosine, we should already know what the answer is going to be, but let's work it out using series. So we get 0 minus 2x over 2 factorial plus 4x cubed over 4 factorial minus 6x to the fifth over 6 factorial, and so on and so forth. We can use what we know about factorials to say that that is negative x, since 2 factorial is 2. 4 factorial is 4 times 3 times 2 times 1, so the 4's cancel, and we get x cubed over 3 factorial Same thing happens here. 6 times 5 times 4 times 3 times 2 times 1. So the 6's cancel and we get x to the 5th over 5 factorial. And that pattern will continue for us. So notice now we've switched from even powers of x to odd powers of x. If we factor out a negative, we get negative x, then we get minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so forth, which is the sum from n equals 0 to infinity of negative 1 to the n times x to the 2k plus 1, because we have odd powers, over 2k plus 1 factorial, because our factorials are odd, which is in fact the expected result. This is the series for the sine function, so we get negative sine of x. All right, we're going to take a look now at an integral. So we want to evaluate the integral from 0 to 0.2 of the cosine of x squared dx. This does not have an antiderivative that we can find using our general methods. You have to use something called the Fresnel cosine integral in order to actually come up with a formula for this. So what we're going to do is we're going to rewrite it using series. So we know that cosine of x is the sum from n equals 0 to infinity of negative 1 to the n x to the 2n over 2n factorial. And that means then that cosine of x squared is going to be the sum from n equals 0 to infinity of negative 1 to the n times x squared to the 2n over 2n factorial, which is then the sum from n equals 0 to infinity of negative 1 to the n x to the 4n over 2n factorial. So now if we want to integrate this, we can integrate the series. So the integral from 0 to 0.2 of the cosine of x squared dx must then be equal to the integral from 0 to 0.2 of this series. With respect to x. And again, like we saw with the derivative, the sum of the integrals is the same thing as the integral of the sum, so we can rewrite this as the sum from n equals 0 to infinity. I can move all the pieces that don't have x's in them to the front, and I get the integral from 0 to 0.2 of x to the 4n dx. So now we have the sum from n equals 0 to infinity of negative 1 to the n over 2n factorial times the quantity x to the 4n plus 1 over 4n plus 1, evaluated from 0 to 0.2. And so when we plug those values in, we end up with this sum. The sum from n equals 0 to infinity of negative 1 to the n over 2n factorial times 0.2 to the 4n plus 1 over 4n plus 1. Now, we want to evaluate this integral with error less than 10 to the negative 4th. So we want our error to be less than 10 to the negative 4th. And that means that because this is an alternating series, we have negative 1 to the n, we know that the error is always less than or equal to the n plus first term. So in other words, we want 0.2 to the 4 times n plus 1 over 4 times n plus 1 times 1 over 2 times n plus 1 factorial. We want all of that to be less than 10 to the negative 4th. And so if we tidy that up a little, we'll see 0.2 to the 4n plus 5 over 4n plus 5 times 1 over 2n plus 2 factorial. We want that less than 1 over 10,000. And it turns out that we don't need n particularly large in order to make this happen. If n equals 0, we're really close, but in fact n equals 1 actually works to make our error smaller than that. You can just trial and error that on a calculator. And so if we use the first two terms, we can say that the integral from 0 to 0.2 of the cosine of x squared dx, our first two terms are going to look like 0.2 minus 1 over 2 times 0.2 to the 5th over 5. So this is when n equals 0 and when n equals 1. And that is approximately 0.19998. So we saw that power series with a very limited number of terms actually gave us a good approximation for an integral that we can't find using analytical antiderivatives. All right, in this example, we're going to determine if the given power series represents a particular function, see if we can identify what that function might be. So we have the sum from k equals 0 to infinity of negative 1 to the k times x to the k over 3 to the k. So the fact that everything is raised to a power here might give us some clue as to how we could simplify this thing. We've got the sum from k equals 0 to infinity of negative 1 to the k times x over 3 to the k, which is geometric. Now, we have to recall that 1 over 1 minus x is the sum from k equals 0 to infinity of x to the k. So a hint that might be useful to us because we have something geometric. And what that actually means is that if we sub in a positive x, so in other words, a negative x, we get the sum from k equals 0 to infinity of negative x to the k, which is the sum from k equals 0 to infinity of negative 1 to the k, x to the k, so changing this to a plus gives us the alternating series. And we have an alternating geometric series here. So we now know that this thing must be the same as 1 over 1 plus not just x, because we have x over 3 here, so we're going to put x over 3 into our corresponding series. We get 1 over 1 plus x over 3. And we can tidy that up. We get 1 over 3 plus x over 3, which is 3 over 3 plus x. So our original series, the sum from k equals 0 to infinity of negative 1 to the k times x to the k over 3 to the k, is actually equal to the function 3 over 3 plus x. And that's probably not true for all x. We would have to find the radius of convergence in order to figure out exactly where these two things are equal to each other. All right, for our last example of how we can use power series, we're going to turn it to human calculators. So most calculators work by doing addition, subtraction, multiplication, and division, which means finding things like the cosine have to be turned into problems like that, and the power series allows us to do that. So here we want to evaluate the cosine of 1/2. using the first 4 non-zero terms of an infinite series? Well, we have one at hand, right? We know that the cosine of x is equal to the sum from k equals 0 to infinity of -1 to the k times x to the 2k over 2k factorial. And we know that this series is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on and so forth. So we'll see how many of those terms we can get to be non-zero by plugging in 1/2. So we're going to get 1 minus 1/2 squared is 1/4 over 2 factorial, which is 2, plus 1/2 to the 4th is 1/16 over 4 factorial, which is 24, minus 1/2 to the 6th is 1/64, and 6 factorial is 720. And so we get, for our first 4 terms, we get 1 minus 1/8 plus 1 over 384 minus 1 over 46,080. And so adding those up would give us a reasonable approximation for cosine 1/2. And of course, we could use the fact that it's an alternating series to figure out how large our error, the maximum value for our error, if we wanted to. We've seen here a number of useful ways that we can use power series. This list is definitely not comprehensive, but we know that we can use them to evaluate limits. We can use them to find derivatives. They're particularly useful for evaluating definite integrals for functions that do not have obvious antiderivatives. We can use them to identify new power series for functions. And we can also use them to identify values of functions using nothing more powerful than addition, subtraction, multiplication, and division.